In this question, a 1,000 milligram dose of drug is given IV, and plasma concentrations are taken for 48 hours. The question tells us that it follows a first-order process, which we'll take to mean that excretion is first order, after the bolus dose. The first-order nature is really only important for the terminal phase, where we're going to extrapolate from the last point to infinity. For the purposes of estimation, the first points don't have to be log-fitted or mono-exponential, as would be the case in an oral drug. So let's take our points and graph them on linear paper first, just to visualize our concentrations. We're going to be doing the linear trapezoid method. If we want to form our first trapezoid, we're going to need an initial concentration. Since our dose is a one-time IV dose, we can use our one-compartment model knowledge and graph all of our points on semi-log paper now. For more details on how to graph on that, we have practice on that with this exact data set in a different video. The apparent initial concentration is 250 milligrams per liter. Now we can start our trapezoids. I personally like drawing the trapezoids on my scratch paper, especially if there are a lot of trapezoids. The area of a trapezoid is the average of the bases, which is the concentrations, times the height, or the width in this case, which is time. I always remember the formula by thinking of the trapezoids as kind of weird rectangles. For our first trapezoid, we take the average of the two concentrations and multiply by the time elapsed, which is 250 plus 185.2 divided by 2 to get the average, multiplied by 3 hours elapsed. The area of this trapezoid is 652.8 milligram hours per liter. The rest of the trapezoids are formed in a very similar way. Now we just need to add these up to get our area from 0 to 48 hours. And that's it for the AUC, right? Well, we forgot our infinitely long tail. But we can estimate the tail with the equation Cn over k. And this k comes from the negative slope of the log graph from before. In our case, that's k equals 0.1. And you have to be careful with this because other problems might say in the question that the data is only log linear after a certain time, like maybe only after 24 hours. In that case, you would get the k from the terminal phase after 24 hours, and not try to fit anything before 24 hours. In this case, all our data is log linear fitted, so we can use our overall k. The equation also needs Cn, which is our last measured concentration. We can just plug in our numbers, and we get a tail area of 20.57 milligram hours per liter. Thanks for watching.